Deep learning is a subdivision of machine learning, which itself falls under the umbrella of artificial intelligence. Machine learning originated from the pursuit of artificial intelligence and initially explored various symbolic and neural network approaches, such as perceptrons. Over time, symbolic and logical methods diverged from machine learning, with a shift towards statistical models and methods borrowed from fields like fuzzy logic and probability theory. Expert systems later dominated artificial intelligence, leading to a separation from statistical approaches. Neural network research continued independently outside the realm of AI, evolving as connectionism, with notable contributions like backpropagation in the mid-1980s by researchers such as John Hopfield and Geoffrey Hinton. In the 1990s, machine learning began evolving as its own distinct field, pivoting its focus from achieving artificial intelligence to resolving practical challenges using statistical, probability theory, and fuzzy logic models. This shift enabled the field to flourish and address applicable problem-solving tasks efficiently. Conversely, data compression shares a symbiotic relationship with machine learning. Systems predicting sequence probabilities can aid in optimal data compression, while optimal compression methods can enhance prediction accuracy. The interplay between compression and machine learning underscores the pursuit of general intelligence benchmarks and highlights how compression algorithms implicitly map data into feature spaces for enhanced similarity computation. Furthermore, the intersection of machine learning and data mining showcases significant methodological overlap, albeit with varied objectives. While machine learning emphasizes prediction based on known data, data mining focuses on unearthing unknown data patterns. Evaluation criteria differ between these fields. Machine learning emphasizes performance in reproducing known knowledge, while data mining prioritizes the discovery of novel insights. Both domains benefit from shared methodologies, with machine learning often leveraging data mining techniques for unsupervised learning or pre-processing steps to improve predictive accuracy. Characterizing the generalization capabilities of learning algorithms remains a current research focus, particularly within the realm of deep learning. Moreover, while machine learning and statistics share methodological similarities, their primary goals diverge. Statistics derive population inferences from samples, whereas machine learning focuses on discerning generalizable predictive patterns from datasets. Machine learning's flexibility in model building, shaped by the data itself rather than preconceived structures, contrasts with traditional statistical analyses that rely on a priori model selection and inclusion of theoretically significant variables. The synergy between machine learning and statistics has spurred the emergence of statistical learning, a hybrid field integrating methodologies from both disciplines for enhanced predictive modeling. Generalization in machine learning refers to the learner's ability to accurately perform on new, unseen tasks after being exposed to a training dataset. This involves building a model based on a dataset from an unknown distribution, enabling precise predictions on novel cases. Computational learning theory, a branch of theoretical computer science, explores the performance of machine learning algorithms. It employs the probably approximately correct learning model and focuses on probabilistic bounds rather than guarantees due to finite training sets and uncertainty in the future. The bias variance decomposition quantifies generalization error, emphasizing the importance of matching the model's complexity to the underlying data function for optimal performance. The complexity of the hypothesis plays a crucial role in generalization. If the model's complexity is inadequate, it may underfit the data, leading to poor performance. Increasing model complexity can reduce training error. However, excessively complex models risk overfitting, resulting in diminished generalization. Learning theorists not only analyze performance bounds, but also investigate the time complexity and feasibility of learning processes, deeming computations feasible if achievable in polynomial time. Positive results demonstrate that certain functions can be learned in polynomial time, while negative outcomes indicate classes that cannot be learned swiftly. Machine learning categorizations include supervised learning, where models are trained with labeled data to derive general rules, mapping inputs to outputs. Unsupervised learning requires algorithms to uncover patterns in unlabeled data, benefiting tasks such as clustering and dimensionality reduction. Reinforcement learning focuses on an agent interacting with an environment to maximize cumulative reward, valuable in scenarios like game playing and autonomous vehicles. While each algorithm type has its advantages and limitations, no single method suits every problem, showcasing the versatility and adaptability of machine learning approaches. A machine learning model is a form of mathematical representation that, once trained on a specific dataset, can provide predictions or classifications for new data. The model's internal parameters are iteratively adjusted during training by a learning algorithm to minimize errors in predictions. The term model can refer to various levels, from a broad class of models and associated learning algorithms to a fully tuned model with all internal parameters set. Model selection involves choosing the most suitable model for a particular task. Artificial neural networks, ANNs, or connectionist systems, simulate biological neural networks found in animal brains. These systems learn tasks through examples without specific programming. ANNs consist of interconnected nodes representing artificial neurons, with signals transmitted between them through connections. The network can process signals and transmit them to other connected artificial neurons. In common implementations, signals are real numbers transmitted between neurons, with outputs computed using nonlinear functions. Nodes are organized into layers with different transformations applied to inputs, with signals traveling from the input layer to the output layer. Decision trees use a tree structure for predictive modeling, moving from observations to conclusions about target values. There are classification trees for discrete target values and regression trees for continuous values. Random forest regression is an ensemble learning method based on decision trees. Support vector machines are supervised learning methods for classification and regression, capable of linear and nonlinear classification using the kernel trick to map inputs into high-dimensional feature spaces. Regression analysis estimates the relationship between input variables and features, commonly using linear regression with methods like regularization to prevent overfitting. Bayesian networks model probabilistic relationships between variables, while Gaussian processes rely on a defined covariance function to compute relationships between points. Genetic algorithms mimic natural selection to find solutions, belief functions handle uncertainty, and rule-based machine learning discovers rules from data. Federated learning decentralizes the training process to maintain user privacy and improve efficiency.